this talk will be about our loss-based method that detects label errors in object detection datasets. So the question is, why do we need such a method? Supervised object detectors are trained based on labels, which are acquired by, for example, humans. Due to various reasons, these labels, as well as training and evaluation based on these labels, are noisy, which in the latter leads to biased benchmarks. If we have a look at the image, which is a test image from the Pascal VOC dataset, we see that only 2 boats are labeled, although significantly more are clearly visible. Our goal is to develop a method that identifies these errors in order to be able to clean them up. We know from the image classification that neural networks are robust to some extent with respect to label errors. For image classification and semantic segmentation, there exist some works that benchmark the task of label error detection, but this does not hold for object detection. Some works deal with label error detection, for instance, by matching labels in video sequences, but without a real benchmark, especially for single input images. What we do, we really set up a benchmark where we compare the performance of different uncertainty-based methods, like the classification entropy, the detection score, or the loss, and we compare the network's predictions with the labels. Since we want to have an automated rather than a manual evaluation of these methods, we simulate label errors on datasets that are as clean as possible. So what we do for this, we use a self-built dataset that has ENlist letters labeled on Cocoa background images, as well as a real public dataset named Berkeley Deep Drive, where the letter is filtered by day and good weather conditions. So the ENlisted dataset can be seen here on top, where we also simulate 4 different types of label errors, namely missing labels. For example, here the missing S, we call them drop. Then class flips that are correctly located but wrongly classified labels, like the P is labeled as an S, and we have correct classified but inaccurate located labels, here the I, which is a shift, and we also have labels that actually represent background. We call them spawns, like the U here. And with our benchmark, we try to detect all 4 different types of label errors. And so for the benchmark, we only look at simulated label errors, but in the end, we also want to count real label errors on commonly used test datasets in object detection, such as Cocoa, Pascal VOC, or Kitty. So our method is based on 2-stage object detectors, where we sum up the instance-wise first and second stage classification and regression loss by comparing predictions with labels. And a sketch of our method is shown here in the figure. So we can find the dropped N. So here we have the input image, here we have our noisy ground truth, and we can find the missing label for N due to a high first stage classification loss, which means the score of the N should be high from the prediction, but there's no ground truth, so we have a high first stage classification loss. The spawned red label here on top is assigned with a high classification loss from the first and second stage, since the assigned predictions should have a score close to 0 in the first stage and an almost uniform class distribution in the second stage, because the region of interest head doesn't know what to predict for this box. And assuming that the yellow label here is a flip, so has a wrong assigned class, results in a large second stage classification loss. And the shifts, which are here not visualized, are addressed by the first and second stage regression loss. And after adding up all the 4 loss components, a high loss score means a high probability of a label error, And the lower this loss score, the less likely a label error. All in all, we compare the performance of our method with the performance of 4 different baseline methods. For the first 2, here the detection score and the entropy, the unique loss score from our instance-wise loss method is replaced by the detection score or the classification entropy of the respective predictions. Note that only predictive uncertainties are considered, and the predictions itself are not compared with the potentially noisy labels, what our method does. Furthermore, we look at the performance of the probability differential here, which is a method from related work and compares the classification of predictions and assigned labels. And the last, the naive baseline, describes the very basic method of simply looking at random images without deep learning techniques and trying to detect all label errors within this image. For our benchmark, we show performance results in terms of area under ROC curve here and the max F1 scores. We observed that our method outperforms all baselines in every experiment, where in general the detection of label errors is harder for the Berkeley Deep Drive dataset compared to our EMList object detection dataset. And yeah, with this, we have shown that especially our method can find label errors very reliably and efficiently. But maybe the more interesting question is whether we can apply our method to find real label errors. And this table shows, yes, we can. So what we've done is we applied the instance-wise loss method and had a view on the top 200 label error proposals. That means we manually reviewed 200 label error proposals for every dataset. Although BDD is already well labeled, we can still find 34 label errors. In addition, we find 96 label errors for Kitty, 125 for Coco, and even 175 for Pascal VOC. For the latter two, it became apparent that labels in particular have been forgotten, so we restricted our proposals to those that had no overlap with a label, resulting in a significantly improved precision. At the end of the presentation, I show a few real label errors that we have found. In the top left corner, we see the input image, and in the bottom left corner, the labeled image. In the bottom right corner, we see the area of interest and the corresponding labels, where the bottom traffic sign here is an incorrect label since it is labeled as a car. Our label error proposal in the top right corner detects this flip and proposes this label to be a traffic sign. And here, the second example, we see that the bottom black part here of this bus is incorrectly labeled as a car. So this means, in this case, we identified 2 label errors. Either we have a spawned car and a missing bus, or the bus was just incorrectly localized, so forgotten this part of the bus, and assigned to the wrong class. So all in all, we found here 2 label errors. And here in this video, you can see the labeled images at the bottom and the label error proposals at the top. So green means that there is no label error, and red means that there is a label error. In a moment, a bus is coming here from the right side, driving in front of these parked cars here in the back. And the parked cars are then no longer visible, but they are still labeled. That means that they are actually spawns. So here these cars are now green, so no label error. And when the bus is in front of them, we have this red color. So we found spawns and label errors there. And finally, I would like to thank the organizers of the conference, as well as my co-authors Tobias, Daniel, Sebastian, Siniša, Karsten, and Matthias.